Okay, so, all right, now it's recording. So if you remember yesterday, what we were talking about was a system with internal work. And it comes about because you have a displacement of one object relative to another. And what we had done at that point is we had started out, just so you're reminded, block A, B are connected, negligible friction. Find VA, VB after B has moved up the incline a distance d. Just for, do you do that? And so this is one of those weird problems that you won't see very often, but it's useful to sort of do an example on. So you have, starts from rest, mass of A is 4 kilos, mass of B is 1 kilo, theta is 30 degrees, mu k between block A and block B is 0.1. The ramp itself between A and the ramp is, there is no friction. Let's see, distance is 0.35 meters. And we went through some effort here just so you remember. It starts from rest, and this is going to be there. We'll define our initial datum as 0. And so the only thing left are the non-conservative work terms that comes from the slip between B and A. So we have T1, T2. T1 is equal to 0. T2, I don't know yet. Then you calculate through, you figure out all of the terms. You have the change in height. And you'll notice here I'm kind of playing a game, but delta XA and delta XB are going to be positive and negative dependent on which direction, but B is going up the ramp, A is moving down the ramp. So the signs will sort of fix themselves in that way. But I also know that the difference between the two is that distance d, which I'm asked to solve for at the very beginning of the problem. So V2 force of friction, which is the only other thing left, is mu k normal AB, mu k mv g cos theta. Put all the terms in there, substitute, and you get the work done, and it's just the distance. So the kinematics, VA equals VB1 or equals 0, and delta XA equals 1/4 d, and delta XB is equal to minus 3/4 d. That's how you get your full d, distance traveled up and down the ramp. So if I do that, I can go back to this and I can say T2 is equal to 1/2 MA VA2 squared plus 1/2 MB VB squared, which is equal to 1/2 MA VA2 squared plus 1/2 MB minus 3 VA squared, 2. Did I do 2's? Yeah. So here what I'm doing is I'm taking the fact that I did already the kinematics for absolute dependent motion, and the relationship between B and A is 3:1. Having all that and getting a nice positive number, I can say that this is equal to 1/2 MA plus 9 MB VA2 squared. V2 is equal to 1/4 3 MB minus MA G d sine of theta. And that's just the change in height, and it's just substituting in that delta XA and delta XB, and recognizing that delta XB is equal to 3 times A. So if you do that, you have the work done you have kinetic energy and you have the change in height. So that is, let me just write that out, T2 and V2. So you have all of the terms that you need and all of the expressions written out in this particular case. So what's your unknown? Your unknown is VA2. You know everything else. You aren't going to solve it this way, but it is a better way to solve it. VA2 is equal to plus or minus square root 2GD over MA plus 9 MB 1/4 MA minus 3 MB sine of theta minus mu K MB cos of theta. So you have from that the full sort of relationship. If you were to solve it, typically what you're going to do is just solve it directly and put numbers in and things will come out all right. Variables tend to be a lot easier to solve for. VA2 then is equal to 0.1424 meters per second. VB2 is equal to minus 0.4273 meters per second. So it's a straightforward application once you have everything written out, once you have all of the displacements correctly done. The tricky bit is really this bit here. And recognizing that one is traveling a different distance than the other. And that's where you're getting your internal work term. So I could look at it just a tiny bit more. So if A And if I looked at the case where just A was sliding down the ramp, then I would get a final velocity, that shouldn't happen, 0.265 meters per second. So what does that tell me? It tells me right away that I got sort of the right order of magnitude. I've got a lot more things happening at VA2 to end up with 0.14 meters per second. And if if you need a rest, maybe you want to go and take a nap. If you add in everything, then you're going to have a lower velocity out. Otherwise, or sort of based on that, it kind of looks like I've got the right orders of magnitude and I've got the right terms in there. Any questions on this one? Go ahead. One, two.
The VA2, are you missing a closing bracket before the
Yeah, probably. It's not important, it's there. When you're solving these, I actually recommend strongly that you do not just look at these problems and try to assume you can solve them. Try them on your own. See why exactly they make sense.
I was just wondering, do they scroll back up to the VA2?
Which one?
How did we convert VB to negative VB?
So we know that velocity of A is going down the ramp, and from kinematics, we know this. And so the relationship is one is going down the ramp, one is going up the ramp. The factor 3 comes from absolute dependent motion. That's all I really want to know from that graph right there. And that's what I'm pulling from it.
So I had a quick question.
Sure.
How will we visualize V? Is it just the relative displacement between A and B?
I'm sorry, VB?
No, just D.
D is the relative. Remember, at the very beginning of the problem, B has moved a distance D relative to point A. And so it's not with respect to a fixed observer, it's with respect to A. Okay, so here I have something a little bit different. I have a problem that is going to include spring forces, friction, and something that's sort of coming to rest. So I have a spring is used to stop a 60 kilogram package, which is sliding on a horizontal surface. The spring has a constant K, which is equal to 20 kilonewtons per meter, and is held by cables so that it is initially compressed 120 millimeters. The package has a velocity of 2.5 meters per second in the position shown, and the maximum deflection of the spring is 40 millimeters. Determine the coefficient of kinetic friction between the package and the surface, and the velocity of the package as it passes again through the position shown. So starting from that, we know that we're going to bring this system to rest. It starts with 2.5 meters per second. It travels along here. It compresses the spring, and that's where you're losing sort of your velocity. So T1 equals 1/2 So I can start out by writing, well, I've got an initial kinetic energy, which is given as 2.5 meters per second quantity squared times 60 kilos times 1/2, and I end up with 187.5 joules. I bring the system to rest. So if I bring the system to rest, then I have the change there. And I'm given two possible sort of displacements. So I can have a minimum displacement and a minimum force in the spring of 2,400 newtons, or a maximum displacement where it goes the additional 40 millimeters, in which case I end up with 3,200. I should have moved it down more. 1/2. I'm going to have to just sort of move around. So I'll have a difference in the work, P min to P max, and that's a negative, and I'll end up with minus 112, joules. So 2,400, 3,200, and 40 millimeters for my delta x. So I have to look at the work done on the spring, and the work is going to be from P min to P max. Now, maybe I should draw this. So I have a normal force, I have the force of friction, and I have mg. I also have, a force of the spring that is opposing motion. So I have to consider all of that in terms of this. And so my work, no surprise, is that work the work is then going to be a combination of both friction work and spring work. So again, I hate work, but there you go. You can also, if you want to do this on your own, and again, this is something I recommend, try and do this as potential energies. So anyways, you've got friction force, you've got spring, calculate the terms. T1 to 2, or T1 plus work 1 to 2 is equal to T2. This is minus 112. And this, oh no, that's minus 112. And this is 377 mu sub k, negative. So you have all of the terms that you need. The only unknown is your mu sub k, which is what you're solving for. You have initial velocity, final velocity, the amount of compression of the spring, and from that you get 187.5 minus 112 minus 377 mu sub k is equal to 0, and mu sub k is equal to 0.2. is a nice number. Any questions on that so far?
For the work on the spring, why is it negative 1/2? Like, why?
What is the work of a spring? So you have kx dx integrated kx squared over 2. Now, what I've done is I've calculated kx and then multiplied it by x. So what I'm writing here is 1/2 kx times delta x, which is the same thing. Which it's 1/2 k delta x. Because it's opposing the motion. So the motion is in this, or the motion is in this direction, the force is in this direction. Go ahead.
You will integrate kx to get the work done by the spring, right?
I integrate kx to get the work done by the spring, so it's kx force delta x. So it's always the same definition, work equals force delta x. So, or force dx, really. And from that, I will end up with 1/2 kx squared. I have to make sure that I'm in the right direction. It's opposing motion, and that's where I get the half. Go ahead. Oh, so if I look at the friction work, so not really well done, but my force of friction is just going to be 60 kilograms time, or its weight. Is it 377? Or did I use the wrong number? Hold on just a second. Oh, yeah, okay, sorry. So it shouldn't, yeah, that's correct. It's 377. I just have to make sure I didn't write something wrong. This is equal to force of friction, which is equal to mu k n times delta x. Delta x in this case is 640 millimeters. You multiply 0.64 by the number you get from the weight, mu kmg, then you will get the 377. Okay. Tuck. Okay, all good. So mu sub k is equal to 0.2. And what I'm interested in also is what will happen when I let this thing return to its original position. So the block compresses the spring, and then it's going to travel 640 millimeters back to its original location. And when it travels back to its original location, I have the same thing happening. And I will fix this later, but part B of this problem. So if I start out at least with this, I have the normal, I have force of friction, which is equal to mu kn, and I have mg. So I have the weight acting down, same thing as before, but the force of friction is acting in the opposite sense, because now the block is moving in this direction. The first part, the block was moving in this direction. So if I put everything together, I end up with The rebound is going to occur with the same compression of the spring, so the same work is done, just a second. And then I have the opposing work done by the friction.
When the spring rebounds, it just rebounds the original compressed length, right? Not the full uncompressed.
I've cut the cables that were holding it in place.
Oh,
Okay?
it's gonna go, it's gonna,
So as far as you're concerned, it travels back 640 millimeters. So that's the distance. Well, you can leave it, for now, just pretend it just stays there. It's okay.
what I was gonna say is the spring goes back to the original, like,
Yes.
the original situation that it was in.
Mm-hmm.
Then we can just find the velocity by calculating the total work done by friction, right?
Plus, you have to include the work done by the spring, because you've expanded the spring.
If the spring was not expanded, if like,
The spring is expanded. So otherwise it wouldn't move. It has to rebound. It has to stretch back out. That's the whole point to the problem. So it compresses, reaches a point, the spring is in a compression state, and then it wants to send the block out. So in this case, it will return to its original state. In the process of doing that, add energy to the system, which you see from a positive.
I'm saying the energy, like the work, the negative work it does in situation one, and the work it does again in the opposite direction, it cancels out. It would cancel out.
Yes. But what happened to the friction?
The friction accumulates.
There you go. Okay. So the end result is that you have 36.5 joules, and T2 plus work 2 to 3 equals T3, and 0 plus 36.5 joules equals 1/2 60 times V3 squared. And so on the return, V3 is equal to 1.103 meters per second. So you lost pretty much 60% of the energy, or 60% of the velocity, which corresponds to a significant drop in total energy of the system. And all of that is lost due to friction. The spring itself is a conservative force. And so the same amount of work or potential that existed at the beginning and the end for the spring is there. The only thing that changes is the friction. Questions? So a more typical problem that you face is the standard, it is the standard pendulum problem put in a whole bunch of different ways. You have 1100 kilogram wrecking ball, and it's released from a beta of 32 degrees. The ball hits the structure, and the wrecking ball forms an angle gamma 14 degrees with respect to the vertical. The length of the cable is 12 meters. Determine the speed at which the wrecking ball impacts the structure. So, you start from rest, you have the thing sort of swing out, and then it impacts against the surface. So, as usual, we're going to do a model that is going to treat the particle or the wrecking ball as a particle, and the only things that are playing a role is the same ones that are playing a role with the kid on a swing. We have weight acting downward and tension acting along this. And tension acts along that line, and I can define an R theta system, in this case, that acts along that line. Now, one of the important things to recognize is that that force P is not acting in the path direction. It's acting normal to the path. And so that term is not going to play a role, and it does no work. So I don't have to worry about it. And one of the things, and the important part of drawing a free body diagram, is to be able to do those kinds of assumptions right from the beginning. And it's also one of the advantages of using this coordinate system. So in this case, I only have conservative forces playing a role. There's no friction. Generally, when you have pendulum problems, you never have friction. And so you can just write this out. Now, the only thing left is to try and figure out where you are at each of those instances. And V1 is just going to be mgl cos theta 1. It's negative because I've defined my datum at the top. V2 is mgl cos theta 2, and that's the second location, so that's the gamma and beta that I defined at the beginning of the problem. And pendulum problems where you have to calculate everything is standard. It's important to be able to do the geometry. It's important to be able to recognize how to calculate the height. It's another reason why it's really valuable as you're solving these problems to draw out what you're dealing with and make sure that the L and this, that you know what you're calculating. So minus mgl cos theta 1 equals 1/2 mv2 squared minus mgl cos theta 2. So V2 is equal to 2GL cos gamma minus cos of beta. So gamma was given to you at the beginning of the problem, beta was given to you at the beginning of the problem. All the terms you need are there. This term, when it comes over to the left-hand side, is going to be positive, so it's cos gamma, and this term will stay negative, and it's cos beta. Solve through, and you end up with 5.36 meters per second. Any questions on this one? This one is kind of a standardish question. And the important thing, and I think it's something to really stick in the back of your head as you're solving these problems, is the fact that you can have forces that do no work, and because those forces do no work, you don't have to include them. This problem would be a little bit more difficult if I switched to an XY coordinate system. Because if I switch to an XY coordinate system, I would include Py, Px, Mgy, and then find out that py, the work done by px and the work done by py cancel each other to 0. But in this form, I just sort of say, hey, it's 0. The other thing, too, is that you should make sure that it always is dimensionally consistent. When I'm doing variables, it's a lot easier for me to see where I might potentially make a mistake, because in the end, I'm just going to put in meters per second squared over times meters, and I'll have meters squared, seconds squared, and I'll have units of meters per second. But if you write them down, you know, I don't see many cases on exams where people write a solution in variables. They tend to write things as numbers. If you write them as numbers, keep your units, it's a lot easier to check and, you know, confirm when you have an error. So again, one of these cases where you have a slightly different case. Crate is unloaded from the top of an RV using a ramp. Determine the speed of the crate as it hits the ground for each of the following cases if the crate is released from rest in the position shown, and if negligible friction between the crate and the ramp, kinetic friction between the crate and the ramp is mu k equals 0.32. You assume that static friction is insufficient to prevent slipping. So you're told in advance, and again, we do have cases where we want you to go through the whole process, but in work energy, we tend to sort of give you sort of this jump ahead. As is usual, I will try and sort of define a coordinate system that goes in the direction of motion. So my x-coordinate is going in the direction of motion. My y coordinate is normal to the ramp. And so I have force of friction, which is acting up the ramp in opposing motion, as usual. I have normal force, which is acting normal to the ramp. And the only thing left is theta, or mg, which is acting at an angle theta with respect to my coordinates. And you're going to spend a lot of time, again, rotating coordinate systems. You've done it with r theta. You've done it with nt. You'll keep doing it throughout the course. And again, I know that you all worry about significant figures. Don't worry about significant figures. Just put everything down until you're done. After that, you can put 2 decimal places or something. All right. Same thing as before, I have my conservation of energy equation, and as I write that conservation of energy equation, I'm going to separate out the potential energies and the non-conservative forces. There we go. as well leave everything as it is. So in terms of the gravitational potential energy, it's a height above, so it's weight times height. On the bottom, it's 0, which is my datum. Right there. So the datum allows me to sort of there. My work, due to non-conservative forces, is entirely due to friction. So it's the length of the ramp, mg cos theta. So mg cos theta is the normal force, L is the length that it travels, mu k is the coefficient of kinetic friction. So I have mgh minus mu sub k mg cos theta, maybe I'll write it like that, times L equals 1/2 mv2 squared. So I have two cases that I want to consider. That is mu k equal to 0, which was the first condition, no friction between the ramp and the crate. So that term over here goes to 0, and I get my regular term which is V2 equals square root of 2GH. Which is 8.29 meters per second. Any questions on that?
Could you just go back up to the measurements?
Yep. This one, so I put onto YouTube the lectures, but I will put on the OneNote for this week, which is just work energy, later tonight or tomorrow, dependent. If I add a friction term to it of 0.32, I'll get a slightly different expression, one that includes the mu sub k, and I end up with 6.44 meters per second. So that kind of gives me some confidence in my results because, one, when there's no friction, I have higher speed at the bottom of the ramp than I have with friction. And so that's something I'll be looking for as I'm solving these problems. Any questions on this particular problem? It's all easy. What do I want to do? I only have 5 minutes, and I don't really want to do another example. So I'm going to sort of go quickly back over some of the initial stuff. So next week, what I'm going to start talking about is momentum. And again, just as a reminder, this week, or last week, we did forces and acceleration. Sum of forces equals mass times acceleration. We're looking at instantaneous values. And so we looked at all of the problems that we're going to look at this week and next week, and we have an approach in the first week that solves everything. But in the second week, we started to look at problems where I want something, force, velocity, or distance. And in those cases, I generally will, or I can always use work energy. If I have a problem next week, and I will, of force, velocity, and time, I'm going to look at it from a momentum point of view. And so what we're going to do is we'll start looking at the third equation, which is sum of forces equals mass dv dt. And we'll end up with three sort of governing equations here. Sum of forces is mass times acceleration of a system. T1 plus work 1 to 2, T2. But now I can add into this expression one thing, which is that T1 plus V1 plus work 1 to 2 non-conservative is equal to T2 plus V2. And generally, when I'm dealing with problems of this nature, I would prefer to solve them as a breakdown of conservative and non-conservative forces. So, for example, this one. This one could have been solved T1 plus V1 plus work 1 to 2 equals T2 plus V2. T1 and T2 would be the same, but it would be 1/2 P min delta x equals V1. V2 would equal 1/2 P max delta x. And solving through for all of these terms are really what you're going to end up doing. So you have to be able to solve through things, solve, basically these kind of issues. The other thing that's really important is to recognize this is a fundamental definition. The tangential force in these cases is the only thing doing work. The normal force does no work. And so it's only the cos theta term in this particular case that does anything, not sine theta. And so you have to look at these problems to try and solve them so that you have something that kind of makes sense when you're dealing with them. Total forces. What else do I want to say about this? This one we haven't dealt with yet, and we won't deal with it really until we get into chapter 6, is the rolling without slip. This one makes intuitive sense. Everybody kind of understands force of friction 0, there's no problem. But the fact is that one of the hard things to understand or accept is that even though you have friction, when you have rolling without slip, because there's no velocity at the point of contact, you have no work done at that point of contact. So we re-derived all of this. Oh, and power. The other thing I kind of want to remind you is that we have force dotted with velocity that gives us power and efficiency, which is kind of useful. Finally, we looked at